So today I'm going to be talking about a topic that I find really interesting, which is a topic about compression, but it's also a topic about why we need such big models. So there's various different interesting aspects to this. As was kindly mentioned, a lot of my research focuses on how do we train models to not just be high test set performance, but to fulfill multiple criteria. So to be fair, to fulfill model interpretability, robustness, and compression. And today I'm going to be actually talking about compression in terms of what it tells us about other properties that the model has. What's interesting is I'm going to be talking about three things. So 3 parts of this talk. So one is I'll tell you why I first got interested in this topic and what first excited me about it. But then I'm also going to tell you about one of the interesting aspects. Oh, my chat has disappeared. Let me bring it back so I can see all the wonderful comments you have. So I see something called "This is your chat pod."
Yeah, whenever maybe question, I can read it for you, Sara. So go on.
Okay, perfect. I'll just go on. It's too bad I won't see your comments, but we'll just keep going,
yes, please.
We'll do it periodically. And then I'll talk about one of the most interesting trade-offs, which is the trade-off between compactness, robustness, and fairness. As well as I'm going to talk about how do we actually leverage this to learn more about really why we design representations a certain way. So let's talk about first the need to compress. So why are we interested in compression in deep neural networks and artificial intelligence? And one of the key reasons is that most of the world uses machine learning in a very resource-constrained environment. So there's very few places where we have unlimited compute and unlimited hardware. Often we're making a trade-off between how do we deploy a model and what's the available compute, memory requirements, battery life, and most of the world is using ML on phones. So this is a very, very constrained resource environment. But this is in tension. Why? It's in tension because gains in test set accuracy have come at the cost of model size. So we have seen that there's actually a race to be bigger and bigger and bigger in terms of model size. Most of recent work on deep neural networks has been using this popular formula where we just throw more parameters at a problem. And this is in tension with our need to then make machine learning accessible and work for everyone. We can see this even in early history. So if we look at one of the first widely used networks, LINET-5, that had a mere 60,000 weights. That was back when everything was petite and small. And now, even if you look at 2012, it's 60 million weights. So some of this is explained by the dimensionality of the input. So when we have something like MNIST, that's a very small image. It's only 28 by 28. And when we increase in dimensionality, we need more parameters to model that dimensionality of input space. So when we increase something like ImageNet, we naturally invite more parameters. But this itself doesn't explain the explosion, because even when we take the same data set, we see ever more parameters. So we go to something like VGG with 138 million. And perhaps most recently, you will have heard about our insatiable appetite for language models that are ever bigger. So we see that our model size is exploding. And this is both in terms of parameters, but it's also driven by the data size that we're attempting to model. So why is this interesting for those interested in compression? So one, it's added urgency to our quest to compress in order to deploy, but it's also a really fascinating theoretical question, which is, even though bigger appears to be better in terms of top-line metrics, it's not well understood why. And for one, that's because there's diminishing returns to adding parameters. So we need to add millions and millions and now billions and billions in order to eke out tiny additional gains. So a good example of this is if we compare Inception v3 to Inception v1, we almost double the number of parameters, but we only gain 2 percentage points in accuracy. We also see many redundancies between weights, which means many weights are doing the exact same thing. So work has shown that a small fraction of weights can be used to predict 95% of the weights in the network. Even more surprising is that most weights can be removed after training is finished. And so this is what we're going to talk about a lot today. Why can we remove 90% of weights? Even if we do it at such a severe level, we only lose 3 percentage points in accuracy. So this prompts us to ask, what are all these weights doing in the first place? Why do we need them if we can then remove them? And so it's not very clear why these additional weights are needed. And this is interesting for a few reasons. It suggests, can we do better than deep neural networks as a representation? Because it appears to be very inefficient. There's so many parameters that are needed to eke out small gains in performance. It also asks the question of, why can't we just train a smaller model to arrive at the same accuracy? And we'll talk a little bit about that later. And to frame this in terms of researchers who are interested in training intelligent agents, we always have the comparison of our biological agents are so efficient. So even if you think about humans, our brain is incredibly energy efficient in comparison. We have specialized pathways, which means we often find it easier to do certain tasks like walk and talk rather than walk and read. So our brain has optimized certain high-speed pathways for certain tasks. We also simulate a lot of what we see, so we don't intake all information, unlike deep neural networks, which see every example a certain amount of time. We run on incredibly low energy requirements relative to our current models. All this to say, this prompts a question of, what are all about the weights in our models doing, and can we do better? Can we be more efficient? And of course, there's very good practical reasons why we care about this. So as you increase the number of weights, you're essentially increasing the number of digits that you're storing, because to do inference, you need to store the floating bit representation of every single weight. So if you have billions of weights, that's a lot more to store. It causes a lot of problems in terms of deployment, and it creates high latency in terms of delivering predictions. And if you're in a low latency requirement environment, so for example, if you want to refresh your browser and see the predictions there, this often is too high a latency. So typically you want 600 milliseconds or less in order to deliver predictions real time. And so we really need to think about, what is the cost of these representations? Also, if we want to think about machine learning being used in a decentralized way, so if we want to train at the edge, if we want to personalize based on private data, then we need to fit models into very severe resource constraints. And that also demands compression. I'm going to stop here. Do we have questions?
Not so far,
well,
but
questions are welcome. If anyone has a question, I'm happy to take them now.
I have a question regarding this. I don't know whether you will come to this or later or not, but the effect of oral parameterization is maybe to get the best, maybe convergence point, something like this.
That's almost an interesting question in the sense that, so convergence, looking at networks with very different numbers of parameters, the convergence properties are impacted if you compare models that are trained very small versus models that are very big, and they converge to different places. However, if you compare a model which starts big and then is iteratively pruned, the convergent paths are very similar, which is interesting in itself. It suggests that often what we need is only a lot of parameters at the early stages of training, and then we find a stable convergence path. We will talk about it a little bit, so I'm happy to talk about when it comes up. Sina says, thank you, everything's great. And Sina says, please continue. Okay, I'm glad. Thank you, Sina, for the nice compliment. Sara says, is it important which weights to discard? Excellent question. So we're going to talk about that right now. That's a very good question to lead into the next section. And I'm glad I can see the chat again. This is very good. So what do we mean by compression? So there's various different techniques. One, which we'll talk about a lot today, is pruning, but I did want to make all of you aware of different important directions of research because you may be interested in pursuing some of these threads. So one area of research is quantization. So you change the bit representation. So remember when I said that one of the difficulties with memory is you have to store all these floating point bit representations. So a lot of research is being, can you just store reduced bit representations? So either from float 32 to float 16, or even int, so binary network style representations. There's also model distillation. So can a large model teach a much smaller model the same amount of knowledge? And that's been very promising. But there's also architecture design. So let's just start by training small. Today, we'll spend a lot of time talking about pruning. So how do we sparsify networks by removing unimportant weights? And Zara's question, is it important which weights to discard? It is, and I'll get to this a little bit, but really, there are many different pruning methods, and how they differ is in the criteria they use to decide this question. So how do you estimate what weights are unimportant, or what activations? So pruning can refer to removing either activations, which is called structured pruning, or to weights themselves, which is called unstructured pruning. Sparsity itself is very interesting because sparse models can easily outcompete dense models with the same parameter count. So this is really what Rahim was asking. He was saying, is the convergent pattern similar? Can you converge? So if you start small, dense, you can't converge the same as large dense. But if you start large and then sparsify, you can converge the same. And you have very similar properties, which is remarkable. It's very interesting from even a theoretical perspective. And then also, it's possible to achieve very high levels of compression with minimal cost. We'll see this and we'll talk about it. So here, this kind of gets to the question of how do you prune and how do you decide what to prune? So one difference between different areas of pruning research right now is when do you prune? So the least competitive approach is that you train and then you just take off the weights and you're done. So you have no recalibration stage. This is called one-shot pruning, and it's actually not very competitive because the weights that remain aren't recalibrated. But the most popular approach, because it's the most competitive with big, large, dense networks, is you iteratively sparsify. So it's been found if you wait a little bit of time, if you start with a big network, you wait a little bit of time, and then you slowly remove weights, then it's far more competitive with a big network. So I want to talk a little bit about starting small. So you just start with a sparse network and you continue to sparsify it, but you're always small. Now, this is important because it's kind of the holy grail for researchers who work in compression. It's kind of our dream objective. And there's a few reasons. It's that you can start small, so training in devices with lower memory is feasible, but you could also go very sparse and large. Rahim says sparsify during training was yes. So this is actually a very good question. Rahim is saying, does regularization count as a type of sparsity during training? And yes, it does, because if you think about very common regularizer terms, they're imposing a preference for low magnitude weights. And if you then threshold that at the end and just remove a certain percentile weights below that threshold, even your L2 norm regularization can count as a form of inducing sparsity. So it's a very good question. So it doesn't have to be per se a pruning technique. We already have an inbuilt preference for minimizing the magnitude of unimportant weights during training. I did want to mention this because although sparse training is this big objective, so starting sparse and continuing sparse, efforts in this direction have still not proved competitive with starting over-parameterized and then pruning, which is the second one. The reason I bring this up, I often find when you're just starting out, it's interesting to learn about what are the ongoing questions that people are thinking about in the field. So a lot of researchers are thinking about this. Why can't we start sparse and then continue sparse? I recently did work in this direction. The work that we did was showing that perhaps one reason that we can't start sparse is that a lot of the decisions that have been made over the last decade about how to design deep neural networks have been implicitly optimized for dense and not starting sparse. And so I did this work. Caleb is the first author in this work, but he showed that there's all these type of preferences, like the choice of activation function, whether you use batch norm, types of optimizers, which can help sparse networks. And so we should be thinking more broadly about how do we train sparse. So Sara says, why the model needs the redundancy at the beginning? So that's an excellent question. This is another open research question, which is why do we need this over-parameterized network if we can just remove it gradually? And the truth is, we suspect it has to do with the early learning patterns. So you need to get into a good optimization space so that you can actually converge properly to the same performance, and that this requires enough parameters to learn the highly frequent attributes early in training. But that being said, as I'm saying this, there's a lot of differences in opinion about this. And in fact, it's a very good question because it's an open area of research. So that's what we're trying to learn, because if we knew why we needed all this extra parameter training, we might also know how we could get rid of all these extra parameters at the beginning of training and just start sparse. So very, very good question. Instead of this goal of starting sparse, the reality is most sparsity methods today introduce sparsity very gradually over the course of training. And these are the state-of-art methods. And going back to this question by Zada, is it important which weights to discard? So it is, but it's also surprising how good very bad simple methods are. So for example, here we have 4 different methods. Magnitude pruning is a very simple method. It just removes weights below a certain absolute value. Variational dropout is a very sophisticated method. It's a Bayesian method. It's very expensive to compute. And you can see here that magnitude pruning is not much worse than variational dropout. So there's a lot of questions in many ways about why are our simple methods so effective? And do we need just better methods for estimation? Also, if you look at random pruning, even something that is that is essentially a random guess what weights to remove, still performs very well. I mean, it's only losing maybe 9% accuracy at 90% removed, which is surprising. So there's also questions here about what are our methods doing and how does this combine with how we choose to remove? So very good question by Sara earlier. So the question that I want to talk about a little bit today, because a lot of my research is focused on it, is that why do we notice so little difference in top-line metrics? How are we able to remove so many weights but still see such minimal difference in top-line performance? Because in many ways, this is what causes the gap in understanding about what all these weights are doing in the first place. So how can networks with these radically different structures have comparable performance? If you even look at something like a ResNet 50 trained on ImageNet, you can remove 50% of weights, and it's basically the same performance, which is surprising. So this is a quote that I like. Don O'Neill says, computers do exactly what they are told, no more, no less. So what this means is that a model can fulfill an objective in many ways while violating the spirit of said objective. And one possibility is that test inaccuracy is not precise enough to measure how pruning impacts the generalization properties of the model. And in particular, in recent work, we go beyond test set accuracy. So I'll be talking about 2 recent papers which really are trying to understand what do we give up when we prune, because we don't observe this in top-line metrics, but maybe we need to propose new measures to understand what is given up. So we ask, how does model behavior diverge as we vary the level of compression? In robustness, so in sensitivity to certain types of distribution shift, but also measure divergence in class level and example level classification. So to do this, we train models at various different levels of sparsity. So 90% sparsity means 90% of weights have been removed. 99 means only 1% of weights remain at the end of training. And we move from an over-parameterized dense model to a model with 99% removed. And what this means is there's some nice properties to set up. So we can precisely vary how radically the weight representation differs. But we have all these models with similar top-line performance. So we're comparing models that have achieved a similar convergence. They're achieving similar loss and top-line metrics, but they've got radically different levels of weights. And this makes it very interesting from a theoretical perspective, because the question then becomes, well, what differs beyond the top-line metrics? So what we find is that sparse models have a far more amplified sensitivity to adversary examples, and that varying sparsity, even though it doesn't impact the top-line metrics, it disproportionately impacts a small subset of the data. Which prompts the question of why. Why is this small subset of the data more sensitive? So let's firstly look at this compression trade-off with robustness. So we look at two different academic benchmarks. So one is ImageNet-C, which is a data set with many different corruptions. So you have ImageNet, and then you add all these corruption layers. And then we have ImageNet-A. So these are adversarial examples. So for both of these, we're asking, well, does a sparse model, after you move the weights, is it just far more sensitive to distribution shifts and to very challenging examples? And we find that yes. So this is looking at the relative sensitivity. So as we increase model sparsity on the x-axis, how is the relative sensitivity amplifying? And so we find that the sparse models have a much lower relative accuracy on these corruptions and on these adversarial examples. And that prompts the question of what makes certain parts of the distribution far more sensitive. So we find that compressed models cannibalize performance on a small subset of classes to preserve and sometimes even improve performance on others. So what's really happening is a redistribution where you cannibalize performance on some classes in order to preserve the appearance of a top-line metric. And we find that this proportion grows. So the more sparsity you add, the more you cannibalize in terms of examples and classes. The question becomes, why are certain classes cannibalized and other classes preserved? And this is where it's interesting to look at the examples that are disproportionately impacted. So if we look at pruning identified exemplars, so these are images where predicted behavior diverges between a population of independently trained compressed and non-compressed models. So if we look here, this is one of the examples that is disproportionately impacted. I want to ask everyone in the audience, so what do you think the true label of this example is? Raheem says, so while we're waiting for people to answer, Raheem says, what pruning schedule did you use? So for that, we use magnitude pruning, and we use an iterative pruning schedule. So we use the state of art. So Zara says table. No, not quite, but good guess. This is actually a toilet seat. So this is an example of a pi toilet seat versus a normal non-pi toilet seat. Hassam says speaker. Amir Hossein says magnet disc. What about this one? What do you think the true label is? In the meantime, Raheem says, is that not because the decrease of reducing the capacity of model? What if you preserve the capacity by adding width and then prune? So that's an interesting question. That amounts to saying, well, can we compare a similar amount of weights but sparse versus smaller amount of weights and sparse? So it's disentangling, is it the number of weights or is it the sparsity impact? I think that's interesting. It wasn't feasible to do at the scale that we did, because if you increase the weight of a ResNet 50 in order to get the same amount of parameters but sparse, it's tricky. It doesn't fit in memory, but I could imagine doing this at a smaller scale with more toy scale experiments, maybe on CFAR 10. So I think that's an interesting extension. That's disentangling. Is it sparsity? Is it the structure versus is it the number of weights, which is a good question. So for this question, we haven't gotten a guess yet. Oh, so Raheem says soda and wine glass. Ahmed says wine. Glass drinks. So this is actually espresso. This is pi versus non-pi. Very good guesses. How about this one? What's the true label for this one? Mariam is typing. So sky, carpet, wool, excellent. So Majid got it correct. This is wool. Excellent. Very, very well done. Yeah, so this is the true label. If you can understand how you might guess this, it's more like the texture. How about this one? Okay, so Shaheen had this guess of windy for the last one. Okay, let's see this one. ImageNet test label, true label. Game board, okay, excellent. This not quite. Game board, chest, blanket. Oh, interesting. So this is actually maize. And you can see that this is, you can see from all these examples, very excellent guesses. Thank you, everyone. You can see from all these examples that these are just very difficult images to guess. And what it turns out is that pi examples are far more challenging for a non-compressed model to predict, which means what's happening is that as you remove weights, even though you're preserving top-line performance, you're first eroding performance on the most challenging examples to begin with. And also what's interesting is that we conducted a human study and we showed that these pies, these examples that are forgotten, over-index on two main groupings. So one is noisy data points. So data is improperly structured, it's mislabeled, it's severely corrupted. Here's some examples of that. So actually in ImageNet, what's interesting is that many of them properly structured mean that there's multiple possible labels that work. So for example, in this first image, the true label is parallel bars. And what the compressed model says is horizontal bars. But you could see this also being a reasonable prediction because there is indeed a horizontal bar in this image. The second is the two labels predicted are corn and ear of corn. And I looked up ear of corn because I did not know this term, to be honest, but the ear of corn is just literally the top of the corn. So it would rarely not be photographed in the same. The final is groom, but the prune predicts suit, which is also true. And what I mean by this is that why we say this is noisy, it's that this is not really a well set up set of images for single image classification because there's multiple labels which could conceivably be correct. And what I think is, and here's examples of corrupted or incorrectly labeled data. So for example, the true label here is restaurant, but you can't really tell it's a restaurant from the image. Or envelope for the second, but the envelope is very small. It would be very hard to understand that's the object of interest. And I want to say that why this is interesting is that, in fact, these noisy examples, it's actually a bad use of all these additional parameters to learn these examples because, in fact, these examples are just improperly structured for the task. They're either mislabeled or they're not really set up well. And so here, it's not clear that this is a good use of extra parameters. And this is an example of bad memorization. But the other group that pi over indexes on is atypical data points. So it would be things like this. So it's things like this toilet seat, which is outside, unusual, or bathtub, or this image of a plastic bag, which is unusual. And here, I do want to say this is a good use of extra capacity. So this is where we would want to think, how do we actually make sure that all those millions or billions of extra parameters, we're actually using them from a typical, but we're not using them for noisy. And what we find is that pies over-index on these underrepresented attributes. In some ways, this is what we're observing. Because we preserve top line, the only way the model can do that is that it cannibalizes performance from low-frequency attributes. So Mohsen says, why not conditioning the pruning compression on the input content? So I think this is a very natural segue from this set of findings, is that what you can do, so this work we did, we released the second paper late last year, but it leads to the question of, now that you know that certain data points are disproportionately impacted, why can't we design methods that forces the model to compress without disproportionately harming? So it's a very good question. Yes, so Ahmed is ahead. So yes, I also think that's a very useful segue of this research direction, which is you can then use Pi to automate how you find mislabeled data. We also find that compression amplifies the impact on underrepresented features. If those are, even if those are protected, it has fairness implications. So we find that on examples like Celeb A dataset, if the low frequency subgroups have protected attributes, pruning will disproportionately erode performance on those subgroups. The same with something like civil comment. So this is a toxicity data set. And so if you have a target label, like predicting which example is target, the pruning will erode performance on that. So here I want to kind of zoom out, and then I want to open up for discussion and kind of further questions. So what I think is most interesting about this set of work and this direction of research is that it's really getting at what are we gaining when we add so many parameters. So our whole ecosystem of what is SOTA now and where resources are put has become invested in adding extra parameters, getting bigger and bigger models. But if most parameters are being used to represent these underrepresented attributes, is this a problem that we can solve more cheaply elsewhere? Would we need as many parameters if we were able to identify what's noisy and clean up the data set? If we were able to surface what's atypical and upright? And that, I think, is a very interesting problem because it gets more in the direction of how do we do adaptive training? How do we get signal about what the model finds challenging early or what all these parameters are doing and allocate capacity better? Because right now, since we delegate the representation to the model, we just say, we don't try and tell the model what features to extract. We delegate to the deep neural network the entire representation. We're also delegating a lot of encoding of information that is not very useful. The model is spending a lot of its capacity learning noisy examples that we could better solve by treating differently in the cleaning pipeline if we could identify them. So if we could use it to identify these examples and route these examples differently, we may be able to use more efficient models. And this isn't just about identifying problematic underrepresented attributes. It's more about all of our data sets and natural image NLP audio data sets follow a ZIF distribution. So what does that mean? It means there's a low amount of high frequency events and a lot of low frequency events, which means that we have to care about how model treats low frequency attributes if we want to navigate the world. It's a core problem that we have to overcome. And so if most of our parameters are spent right now learning these low frequency events, if the majority of our capacity is used for low frequency, it's not a very efficient way for us to learn how to represent the world. We need a cheaper way and more efficient way. And thinking about the effect of compression on these low frequency attributes gives us insight into perhaps we need to represent these differently since they're costing so much. So to the wonderful questions by Ahmad, so can we use Pi to find mislabeled data? So another of my, the quotes I like is if you can't measure it, you cannot improve it. So I do think one of the uses of Pi is to surface, to help audit, to surface a tractable subset of the most challenging, these challenging examples. And one of the reasons this is so important in the real world and more research like this is that labeling is very expensive at scale. So it's often infeasible to do comprehensive labeling. And it's often difficult to be able to do that for sensitive features. So if we want to audit harm, for example, it's hard to do that for all the features that we care about and all proxy vehicle features. And what we found is that Pi is a valuable and supervised protocol for surfacing examples that require additional auditing or constraint strain training. It also provides a target for directly optimizing for models that are both compact and relatively more robust and fair. So I think this was perhaps the question that Mohsen was alluding to, this idea that can we then condition the pruning compression on the input content? I think it's an important direction where we can constrain the pruning to have similar rates of impact across different subgroups. So there's been work that's built upon ours since and is really interesting. So for example, this is a group of researchers at the University of Utah that shows that distillation objectives can combined with pruning can help improve these trade-offs. This is also another recent work which has shown that knowledge distillation coupled with pruning can improve trade-offs. What I want to mention is that this is a very interesting work, which if you remember our results on robustness, we found that if you prune, the sensitivity to these ImageNet C, ImageNet A is amplified. So the models become much more sensitive. So this group built upon our work, and they explicitly designed a pruning method which can improve some of these robustness measures. And I thought that was a very interesting next step in this series of research, is that if you know that your pruning methods are amplifying harm, you can actually explicitly design to achieve a better trade-off. It's a very interesting area or direction of research. So I'm going to stop here.